You ever heard of the Fermi paradox? It questions why, despite the odds for extraterrestrial life existing in our galaxy are exceedingly high, we have yet to find any. There's a plethora of hypotheses as to why that is, such as that, due to the size of our galaxy, other life is too far away for us to have found yet. A creepier postulation is the zoo hypothesis, in which other intelligent species know we're here, but are just watching us like some cosmic ant farm. And of course, there's the sobering idea that we haven't found extraterrestrial life because we are, and always have been, alone in this universe. But there's one hypothesis that depresses me and simultaneously boosts my ego. It's called the Great Filter Hypothesis, and the idea behind it is that the universe is a chaotic place and it's constantly trying to kill us. Earth has tried to choke us out with carbon dioxide and toxic volcanic gas, or drown us with melting glaciers while desalinating the oceans. Space itself even took a crack at it when it hurled a giant rock at us once, but luckily it just killed some lizards. I don't know if you know about that time. Anyway, odds are all life on our pale blue dot should have been wiped out by now, and you wouldn't be watching this video. And yet, here we are, after more than 4 billion years of evolution, looking into the cosmos for others in the hopes that we are not on our own. Enter our next door neighbor, Mars. In terms of distance from the Sun, it comes just after Earth at 144 million miles. It's got 2 moons, Phobos and Deimos. Matt Damon has been there. Oh, and it probably harbored life. No biggie. You might have heard recently that some new evidence was found on Mars, potentially indicating life in the distant past. It was kept somewhat on the down low because of certain oopsies that have happened in the past, and a lot of the people that did end up hearing about it brushed it aside because talk of planets with the potential for life seem to be pretty commonplace these days, and as we all know, nothing ever seems to come of it. But I'm here to tell you guys that this is probably the best evidence towards life having existed on Mars that has ever been discovered. What you see here is a photograph taken by the Mars rover Perseverance back in July 2024 in a dried up river delta within the Jezero crater. It's a large sedimentary rock with these bizarre spots that have been given the nickname Leopard spots. These are the focus of all the excitement. Now, before you click off the video and spread the good news, I need you to know that this is not 100% definitive proof, as abiotic processes can't be fully ruled out, but I'm cautiously optimistic about this, and I'll tell you why. But before I can do that, we need some background information, specifically what scientists look for in the search for extraterrestrial life, and the criteria that this new discovery on Mars checks off. If you already know about the important factors that indicate potential life, skip to the time on screen. But for the rest of you, strap in. Class is in session. When we look for exoplanets, we look to the stars. Of course, even the closest stars to our solar system are several light years away, and so appear very small. The detailed images of stars and exoplanets we see online are not photographs, but rather digital renditions of what they most likely look like. Now, after we find a star, we find planets by analyzing the data about the star's light. If we notice it dim ever so slightly, that tells us an object, potentially a planet, has passed in front of it and is blocking some of the light. From here, we can tell how far the planet is from its star based on how long the light is dimmed. This informs us on how long it takes to orbit its star, and taking that information with its estimated size, we get an accurate distance. For planets potentially containing life, we are looking for those within what is known as the habitable zone, or HZ, colloquially known as the Goldilocks zone, where the conditions are just right for water to exist as a liquid. In other words, the temperature on the planet's surface should be between 0 degrees Celsius, water's freezing point, and 100 degrees Celsius, water's boiling point. Obviously, it won't be within that range everywhere all at once. It's not even like that on Earth, but still. Now, because the intensity of heat from stars can vary, the habitable zone is not the same for every solar system. but it's a relatively easy task for us to figure out where it should be. For those curious, our solar system's HZ is roughly between 0.85 and 1.7 astronomical units, or AU, with 1 AU being the distance from the Sun to the Earth. All life on Earth requires liquid water in some capacity, and we know through geological and fossil evidence that almost immediately after conditions on Earth stabilized and liquid water became present, living things started popping up. Another important criteria is if an exoplanet has an atmosphere, and more importantly, what said atmosphere is made of. To accomplish this, we use something called spectroscopy. Spectroscopy is the study of how light interacts with matter at various wavelengths. There's a good chance you did this in high school, but in case you need a refresher, the basic idea is to shine varying wavelengths of light through matter to determine what molecules are present. Different molecules have different signatures that appear at different wavelengths. For example, here's what a few organic compounds look like in an IR spectrum. The spikes with labels you see show where the labeled chemical bonds start appearing. Astrobiologists search for specific gases in exoplanet atmospheres that could indicate life, with there being certain sought-after characteristics. One is a gas that breaks down or bonds with other compounds quickly, and seeing it would indicate that there is a continuous source, possibly living things. The other obvious one is finding gases that we know on Earth to be produced by living things. Of course, these aren't dead giveaways, as virtually every gaseous biosignature we know of has ways it could be produced inorganically, but extraterrestrial life is still a potential reason. Some of the gases we keep an eye out for are methane, carbon dioxide, especially if there are seasonal fluctuations in its concentration, and of course, oxygen gas. The detection of liquid water would indicate the existence of an atmosphere as well. The atmosphere wouldn't have to be very thick at all, about 612 pascals, but it's something. We can find it by looking for water vapor using spectroscopy, but another way is with something known as ocean glint, whereby light from an exoplanet star reflects off of water on the surface of the planet in question. Also, if we could hypothetically see the planet in question and identify either active or dried up bodies of water, like lakes, rivers, and oceans, we know that the planet had an atmosphere, or currently has one, for those geological features to exist. The last big feature an exoplanet should have is a magnetosphere. We detect this using radio telescopes to see how a planet interacts with the solar wind from its star. The magnetosphere is generated by the movement of a planet's molten iron core, creating electric currents in a process known as geodynamo. It's similar to how electricity is made by spinning magnets, but on a much larger scale. I think. I'm not a physicist, or a geologist, or a meteorologist. Anyway, the magnetosphere protects a planet from solar wind from its star, which is full of radiation. Radiation is terrible for living things because, to put it simply, it breaks apart DNA and RNA. Obviously, that's bad. So for DNA and RNA-based life to form and evolve, a planet needs a magnetosphere. Also, a magnetosphere can be pretty important in having a thick atmosphere. A planet can have an atmosphere without a magnetosphere, but the solar wind will strip it away over time. With all of that said, let's go over the features that Mars has. Mars has a star, and is the fourth planet in its solar system. Our solar system. Sometimes you can look up at the night sky and see it with your naked eye. It falls within the HZ, if somewhat close to the outer edge. Due to its elliptical orbit, it varies between 1.52 and 1.66 AU from the Sun. And if you'll remember, both of these values are within the HZ of our solar system. We typically picture Mars as a desolate, frozen wasteland, which is partially true as it has an average temperature of -80 degrees Fahrenheit. But you may be surprised to know that during the summer at the equator, the surface reaches 70 degrees Fahrenheit, practically room temperature. Mars has an atmosphere, but it's very thin, about 600 pascals, which isn't quite thick enough to have liquid water. It's about 95% carbon dioxide, with 4-ish% being nitrogen and argon, and trace amounts of CO2, oxygen, and water vapor. Just so we don't jump the gun on that oxygen, which here on Earth is made by photosynthesis, the oxygen on Mars is formed when the trace water vapor is hit with ultraviolet light, which is exposed to more than Earth due to its thinner atmosphere. The hydrogen atoms have their chemical bonds broken by the UV light, and the lonely oxygen atom will find an equally lonely oxygen atom, and they will be happy together. Isn't that sweet? Now on to liquid water. It isn't on the surface of Mars right now, and we know that because we can see its surface without any of the fancy tricks we already discussed. But we know it most definitely had liquid water in its past. These are all real images of Mars' surface, showing various dried up bodies of water. It's usually not enough to go off of just looks, but for this, we can make an exception. No other geological process in existence makes formations like these, but in case you wanted more evidence, rovers have found signs of erosion and sediment buildup, both of which are caused by liquid water. And if there was enough liquid water to create bodies of water this large, the surface was most definitely a higher average temperature than it is now. As for a magnetosphere, it doesn't have one. Not right now, at least. But we can see evidence of previous tectonic activity, which is caused by the motion of a molten iron core of a planet. And as we've previously discussed, that motion is also what creates the magnetosphere. With all that said, it becomes clear Mars used to have the right conditions to support life. Within the Goldilocks zone, thick enough atmosphere to have liquid water, an incredible amount of said liquid water, and a magnetosphere. So what happened? Well, Mars is still within the HZ, so that's not the issue. So what else could it be? Well, without the magnetosphere, solar wind would strip away the atmosphere over time. A thinner atmosphere means Mars' surface wouldn't retain heat as well, and would become too thin for water to remain liquid. And without liquid water, yeah, life wouldn't stand a chance. Next question. How long would life have to first evolve and exist on Mars? Well, much like the rest of the solar system, Mars formed around 4.5-ish billion years ago. Very shortly after that, about 200 million years later, Mars had a lot of liquid water on its surface. That's evidence of a thick atmosphere, which is evidence of a magnetosphere. Mars' magnetosphere likely existed until about 3.9 billion years ago, perhaps even more recent than that, which gives us roughly 400 plus million years for life to have evolved, with NASA saying it was potentially even longer than previously estimated. Now, is this enough time? Well, let's go off of our only real-world reference, Earth. It formed at about the same time as Mars, but had a much longer unstable period, known as the Hadean Eon. It was full of extreme temperatures, both warm and cold, frequent asteroid impacts, a toxic atmosphere, and possibly no magnetosphere. This period ended about 4 billion years ago, with the first evidence of life being 3.8 billion years old, but had definitely existed before that, meaning it took life less than 200 million years for life to evolve once Earth stabilized. This is much less time than life had to potentially evolve on Mars. But what kind of life could have evolved? Well, eukaryotes first evolved after about 1 billion years, meaning Martian life never reached an analogous phase. In all likelihood, it never got past prokaryotic life. Now, we just have to find some. In the past, we thought we found evidence for it, but every time it turned out to be false positives. Let's go over a couple of those times. The search for life on Mars really took off in the late 1800s, when people thought they had found liquid water in the form of canals, but these turned out to be optical illusions. Nevertheless, we discovered evidence of liquid water in Mars' past, based on all the dried up rivers and other watersheds. And liquid water is a very good indicator of life. In 1984, a Martian meteorite found in Antarctica, known as Allen Hills 84001, was found to have features that resembled fossilized bacteria, initially giving credence to panspermia, but they turned out to have been created by abiotic processes. Other meteorites from Mars have been discovered since then, but none have turned up with any smoking guns. But I've drawn out this video for way too long. Let's get to what you all came here for. These are the spots in question. They're made of iron-rich minerals known as vivianite and greigite. Now, both of these can be made by abiotic processes. However, the conditions for such processes are specific and do not fit the location the spots were found. They can form abiotically in very hot places, such as around hydrothermal vents or in acidic conditions. The location of the Leopard spots is in a dried up riverbed, so not a hot location, and not an acidic one either. The only other way we know of for vivianite and greigite to form is via electron transfer reactions, or in other words, living things. We can't rule out for certain that these deposits were made abiotically. However, according to several experts, this is likely the strongest evidence we have for life on Mars. How would we confirm this? Well, we would have to get these samples back to Earth. Perseverance, the rover that found the spots, has been packaging up samples it finds and leaving them on the surface to be picked up by a robot at a later date. Unfortunately, the mission that's supposed to be picking these samples up hasn't even launched yet, and probably won't until the 2030s if we're talking optimistically. Maybe the discovery of these leopard spots will generate some kind of delayed excitement and get that mission sped up, but I wouldn't hold my breath. But if we do eventually get those samples back and it turns out that, yes, they were indeed created by living things, that could mean a few different things. One option is panspermia. We already learned of Martian meteorites found on Earth, so it could be possible that one that just happened to harbor life managed to make its way to Earth billions of years ago and hasn't been discovered because it is, since been cycled through the Earth's mantle. The reverse is also possible, where life originated on Earth and made its way to Mars, but I'm not entirely sure the timeline works out quite right this way around. The final option is that life evolved independently on both planets, very possibly existing at the same time, but too primitive to be aware of each other's existence. This is the most exciting option for me, and likely the rest of the scientific community, because it drastically increases the odds that life should be extremely abundant in our universe. I mean, life springing up twice in the same solar system? Imagine how many of those Earth-like planets we found throughout the decades have life on them as well. But, of course, it begs the question, why haven't we found it? And that brings us back to the Great Filter hypothesis. The reason we haven't found any life outside of our own planet is because nowhere else that we have looked was life able to survive its bottleneck events. 5 times in Earth's past, more than 50% of all living things went extinct in a relatively short time period, and it would seem that on Mars, life didn't get so lucky. Due to the loss of its magnetosphere, the thinning of its atmosphere, or all the rivers, lakes, and oceans drying up, every last hypothetical living thing on Mars died off, never learning that its planetary neighbors had to go on without them. And now here we are, learning that we were likely not alone. Not just in the universe, but even in our own solar system. And so we must continue the search for extant life elsewhere. Will we ever find it? Well, we definitely won't come into direct contact with it for as long as I live, as the nearest Earth-like planet is more than 4 light years away, and there's no way we'll get there before I'm long gone. But I have faith in the human race, that we will one day become a multi-planetary species, first terraforming Mars and maybe some of the moons in our solar system. The idea is that we will one day no longer be dependent on our sun, and that humans will have a place to migrate to once Sol becomes too dangerous to live around. Doing so would make our species effectively immune to the Great Filter, as, to put it simply, we wouldn't have all our eggs in one basket. Life on Mars may not have survived its bottleneck events, but I'm cautiously optimistic to say that Earth, and more specifically humans, did. And I hold out hope for the day that we meet others that have beaten the cosmically stacked odds. That's all I got for you guys today. You all have yourselves a good one, and I hope you learned something.